if we are to solve non-homogeneous higher order equations where the g of x cannot fit any of the portions on the table for the trial particular solution, then we are going to move into another process, the variation parameter, specifically the use of Wronskian of functions in solving such. So that is why we are representing here the Wronskian of functions, specifically for these two functions, e to the power of x and e to the power of negative 3x. Let's assume that this will come out later on in the process and Wronskian is needed. How do we show the Wronskian of functions? We have two functions here. That is why we can use here a specific matrix with two columns. Why matrix? Because the Wronskian of functions is simply the determinant of a matrix following or using these functions here. So as mentioned, we have two functions, so we have two columns. So if we have to come up with the matrix, these are the first entries. Okay? Now, the next row would be the first derivatives of the entries or the functions. Now, this is also supported by this idea because we know that when do we end up with our derivative? Because if there are more, we can always continue to nth number of derivatives. But since we have the formula of n minus 1 telling us the number of times we are going to solve for a derivative or the highest order of derivative, we have two functions minus 1. This is an indication that we really end up to the first order derivative. Hence, the first order derivative of e to the power of 3x is itself times, times, because our angle here, or I mean, not angle, exponent could also be, according to the chain rule, must also be derived. So the derivative of that is 3. Now, for the second column, it's also e to the power of negative 3x. And the derivative of the exponent is just negative 3 or times negative 3. Hence, our matrix now, and it's a 2 by 2 matrix as mentioned because we can only get determined if we have a square matrix. E to the power of 3x, e to the power of negative 3x. We have here 3, e to the power of 3x, and negative 3, e to the power of negative 3x. This is our matrix, and the determinant of this is simply our Wronskian. So the Wronskian of e to the power of 3x and e to the power of negative 3x is again the determinant. So we follow this. We can use this portion from upper left to lower right. That's a positive. The result of the product is positive minus this portion here. So let's start with the red. E to the power of 3x times negative 3 e to the power of negative 3x. Then, you're going to subtract the result of the other diagonal. 3 e to the power of 3x times e to the power of negative 3x. So, we'll have here this result. Of course, negative 3 e to the power of, let's add exponents. Of course, you need to add exponents. You will have here 3x. We are adding exponents because we are multiplying the same base e. So that's 0. Minus the other side, 3 e to the power of 0 as well. So how would this go? We know that this is negative 3 and that's equal to 1. Okay, any expression raised to 0 is just 1. You also have minus 3. This is also equal to 1. So with this, the Wronskian of the given functions is negative 6. And if we are, again, intended this to be part of a solution of a non-homogeneous higher order equation, we are going to use this value in other versions of the Wronskian. Thank you very much for watching.